We will now return to our algebraic calculation of distance traveled and relate it to what we discovered graphically. As we have done before, we will use s of t for position and v of t for velocity. And remember that v of t is the derivative of s of t. We found graphically that the change of s of t from t equals a to t equals b is the area under the graph of v of t from t equals a to t equals b. But this isn't only true for velocities and positions. In general, if f of t is the derivative of capital F of t, then the change of capital F from t equals a to t equals b equals the area under the graph of little f of t, the derivative from t equals a to t equals b. What this means is that we can figure out information about a function simply by knowing its derivative. Let's now return to our example where the velocities of a runner starting a race are given by the following graph. And again ask the question, how far did the runner travel from t equals 0 to t equals 6? Knowing what we know now, we can calculate the change of position, that is, change of s of t, from t equals a to t equals b, as the area under the graph of v of t from t equals a to t equals b. But how do we find the area under this graph? Unlike our last example, it's not simply made up of triangles and rectangles. So we'll have to return to our approximation. Let's now remind ourselves of how we calculated our approximation in this example previously. Recall that the velocities were given by the following table, and we wanted to know how far did the runner travel from t equals 0 to t equals 6. In our new language, that's saying that a equals 0 is our starting time t, and b equals 6 is our ending time t. Recall that we found two approximations for how far the runner could have traveled. We started by finding the overestimate, the furthest the runner could have traveled. To do this, we broke our 6-second interval into 3 2-second time intervals. Starting with the first time interval, we said that the runner traveled at most 8 feet per second for the first 2 seconds, so they traveled at most 16 feet. We represented this as a rectangle of height 8 and width 2, giving an area of 16, representing the 16 feet traveled. Then we put this on our graph over the time interval from t equals 0 to t equals 2. So this gave us a graphical interpretation of the fact that the runner traveled at most 16 feet in the first 2 seconds. Next, we looked at the time interval from t equals 2 to t equals 4. Here, we used that the runner traveled at most 14 feet per second for 2 seconds, so they traveled at most 28 feet. And we represented this with a rectangle of height 14 and width 2 for an area of 28, representing the 28 feet that the runner could have traveled. We then put this on our graph over the time interval from t equals 2 to t equals 4 to represent that the runner traveled at most 28 feet in that time interval. Lastly, we looked at the time interval from t equals 4 to t equals 6. Here, we calculated the distance traveled as 18 times 2, since we knew that the runner traveled at most 18 feet per second for 2 seconds, giving 36 feet. We represented this with a rectangle of height 18 and width 2 for an area of 36. We then put this on our graph, representing that the runner traveled at most 36 feet over the time interval from t equals 4 to t equals 6. And our approximation was that the total distance traveled was roughly the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle. We will now be a little more clever about how we write these. Remember that A1 was calculated as 8 times 2 because it was the velocity at 2 times delta t. A2, the area of the second rectangle, was calculated as 14 times 2 because 14 was the velocity at 4 and 2 was our delta t again. Finally, the area of the third rectangle was calculated as 18 times 2, which came from the velocity at 6 times delta t. So what's the significance of the times 2, 4, and 6? 2 is our starting point A, which is 0 in this case, plus delta t, which is 2. 4 is our starting point A, plus 2 times delta t. And 6 is our starting point A, plus 3 times delta t. Substituting these in for 2, 4, and 6, we can write the distance traveled, A1 plus A2 plus A3, as V of A plus delta t times delta t, which is A1, plus V of A plus 2 delta t times delta t, which is A2, plus V of A plus 3 delta t times delta t, which is A3. The reason that we make this difficult change is that when we look at delta t getting smaller and smaller and smaller to make our approximation better and better and better, it will be easier if we have our calculation in terms of delta t. Let's now make our first step at making this approximation better by, instead of taking 2-second time intervals, we look at 1-second time intervals. Previously, we calculated our overestimate as 4.5 times our delta t, which is 1, plus 8 times delta t, plus 11 times 1, plus 14 times 1, plus 16.5 times 1, plus 18 times 1, giving a total of 72 feet. Interpreting this graphically, we have that the distance traveled is roughly the area of the first rectangle, A1, plus the area of the second rectangle, A2, plus the area of the third rectangle, A3, plus A4, plus A5, plus A6. And as we did last time, the area of the first rectangle, A1, is our velocity v at A plus 1 delta t times delta t. Remember here that A equals 0 and delta t is 1. So A plus 1 delta t is simply 1, which means we calculated the area as v of 1, which is 4.5, times delta t, which is 1. We calculated the area of the second rectangle as v of A plus 2 delta t times delta t. The third rectangle as v of A plus 3 delta t times delta t. The area of the fourth rectangle as v of A plus 4 delta t times delta t. A5 as v of A plus 5 delta t times delta t. And A6 as v of A plus 6 delta t times delta t. At this point, we can start to see a pattern of how the area of each rectangle is computed. But it's getting very messy, so let's try to clean it up. We will write Ti as A plus I times delta t. In this case, T1 is 1, T2 is 2, T3 is 3, and so on. So the area of the ith rectangle, AI, is v of Ti times delta t. This simply means that the area of the first rectangle, A1, is v of 1 times delta t. The area of the fourth rectangle, A4, is v of 4 times delta t. But again, writing it in this abstract way will allow us to understand what happens as delta t gets smaller and smaller. Because we know to get a better approximation, we want to compute this for larger n, which means that we have smaller delta t's. If we break our 6-second time interval up into n smaller time intervals, the distance traveled will be the area of the first rectangle plus the area of the second rectangle plus the area of the third rectangle plus the area of the fourth rectangle all the way down the line plus the area of the nth rectangle. But this is getting tedious just to say. To get a cleaner way to write it, we use the following notation. We say that the distance traveled equals the sum of I equals 1 to n of ai. This simply means what we wrote above. All of our a's added up, starting at a1 and going all the way up to an. But on the last page, we figured out how to calculate each of these ai's. We said that ai is the velocity at ti times delta t, where delta t was the length of our entire interval, b minus a, divided by n, or in this case, 6 divided by n. And ti is our starting point a plus I times delta t. So we get that the distance traveled is roughly the sum from I equals 1 to n of v of ti times delta t. The question that remains is, how do we change our approximation into an actual equality? We saw before that for our approximation to get better and better, we need to take the number of intervals to be more and more. And as we take more and more intervals, eventually we need to take the limit as n goes off to infinity, which just becomes the area under the graph. So we get that the distance traveled is the limit as n goes to infinity of the sum from I equals 1 to n of v of ti times delta t. So to summarize, we found that the distance traveled from t equals 0 to t equals 6 is found as the limit as n goes to infinity of I equals 1 to n of v of ti times delta t, where delta t is 6 minus 0 over n, and ti is 0 plus I times delta t. Note that the sum from I equals 1 to n of v of ti times delta t is called the right-hand sum. We call it this because we use the rightmost point on each interval. Similarly, we have the left-hand sum, which is the sum from I equals 0 to n minus 1 of v of ti times delta t, because it uses the leftmost point of each interval. The left-hand sum is what we used as our underestimate. But it doesn't matter which one we use, because the limit as n goes to infinity of the right-hand sum equals the limit as n goes to infinity of the left-hand sum. And once we take these limits as n goes to infinity, we call these Riemann sums. Let's now generalize what we just saw. We found that the distance traveled from t equals 0 to t equals 6 is given as the limit as n goes to infinity of the sum from I equals 1 to n of v of ti times delta t, where delta t is 6 minus 0 over n, and ti is 0 plus I times delta t. More generally, the distance traveled from t equals a to t equals b, that is, the distance traveled over any time interval, is calculated as the limit as n goes to infinity of the sum from I equals 1 to n of v of ti times delta t, where delta t here is the length of our interval, b minus a, divided by n, the number of time intervals we're splitting it up into. And ti is our starting point a plus I times delta t. To make this most general, we want to look at capital F, whose derivative is little f. Here, in the general sense, The change in f of t from t equals a to t equals b is given as the limit as n goes to infinity of the sum from I equals 1 to n of f of ti times delta t, where delta t is just as above, b minus a over n, and ti is a plus I times delta t. Let's remember that while we can find the change in f of t from t equals a to t equals b as the limit as n goes to infinity of the sum from I equals 1 to n of f of ti times delta t, we can also calculate it as the area under the graph of f of t from t equals a to t equals b. Note that since what we have written on the right is so tedious, we give it the following notation, which is called the definite integral. We say the integral from a to b of f of t dt is called the definite integral of f of t from t equals a to t equals b. So why do we care about the definite integral? Remember that in chapters 2 through 4, we found out information about f prime of t when we only knew the original function f of t. With the definite integral, we can find out information about f of t when we only know its derivative, f prime of t. It is very common in applications that it's easier to find the derivative than the actual function, and this gives us a way to use that information about the derivative to understand the original function. The problem is, the integral is hard to compute and involves a limit. This is similar to the derivative. The difference is that for the derivative, we spent a long time learning how to calculate them in very efficient ways and not using our original definition. This can be done for the integral as well, but we don't have a long enough time left in our semester to do the same here. Typically, techniques of calculating integrals is taught in a Calc 2 course. So instead, we will use a calculator to calculate these definite integrals. Since many of you will be using different calculators, there are links to YouTube videos on Moodle on how to calculate integrals using a graphing calculator. I listed common calculators you may have. If your calculator is not on the list, let me know and I will add it.